Hypothalamus Artificial Intelligence, HI, and Research Center for Advanced Decision Technologies, RCA-DET, a division of HI. Digital transformation powered by real-time autonomous and intelligent algorithms. Present. OPTEX, Optimization Expert System, the artificial intelligence produced by HI, that manufactures decision support systems. Making high-complexity large-scale mathematical models without programming. Imagination is the beginning of creation. You imagine what you desire, you will what you imagine, and at last, you create what you will. Developing mathematical models software. Traditional approach. Traditionally, the implementation of computer solutions, aimed at highly complex mathematical modeling, is conceived as a process that integrates a team of programmers to carry out mathematical modeling activities, and the programming of associated computer programs. This approach entails high development and maintenance costs, especially when it comes to solutions tailored to the end customer. This gets more complicated as the mathematical models get bigger. The traditional way, it is impossible for infinite-sized models. A computer programmer can produce a limited lines of good source code per period. OPTEX, the HI's cognitive robot, can produce infinite lines of perfect source code in seconds. Artificial brain, a new integrated vision of mathematical programming and artificial intelligence. The history of commercial digital computing started in 1946, when the ENIAC, the first general-purpose computer based on electronic circuits, was presented to the public. The primal simplex algorithm was developed by the American mathematician George Dantzig in 1947, and it can be considered the starting point of applied mathematical programming, and the birth of computer-oriented mathematics. In 1962, the Dutch mathematician Jacques Benders publishes his theory of partition that is a transcendental step, not the first, in parallel computing, aimed at solving complex mathematical problems, dividing them into more elementary subproblems. In 1983, Tony Van Roy created the cross-decomposition approach to solving large-scale optimization problems, partitioning and decomposition techniques, and mixing different types of methodologies, such as Lagrangian relaxation and Bender's theory. The growth of informatics has impacted the evolution of advanced mathematical programming, orienting it to parallel processing, whose most elementary level is at the level of parallel operations on a CPU. The following two levels of parallelism are related to algorithm, and the process of decomposition and partitioning of major mathematical problems. The future will be the use of quantum computers. The development of specialized algorithms for this type of computing is already in process. Currently, the new optimization algorithm's vision is its distribution through multiple processors using cloud computing jointly with edge computing. HI is the creator of the concept of artificial entrepreneurial brains, which is supported by the development of parallel thinking, when a complex system must be analyzed. The artificial brains corresponds to the scientific foundations, more specifically mathematical fundamentals, that allow to connect multiple mathematical models, algorithms or robots, exchanging information between them to obtain a common goal, and act as holistic intelligence of the organizations, or parts therein. Like the human brain, the artificial brain is composed of the following artificial components: neocortex, hypothalamus, and hippocampus. This evolution may be summarized as the shift from artificial intelligence to augmented artificial intelligence. For the year 2000, approximately, the decision support systems, DSS, were conceptualized as a set of mathematical models that exchange information between them, working offline. The first commercial supply chain management solutions was developed based on DSS concept. The artificial brains is the evolution of DSS under the Industry 4.0 revolution that is conceptualized as a set of mathematical models that exchange autonomously information between them, working online, using distributed optimization. Artificial brains are backed by the technological capacity of computing. It is traditional to associate mathematical modeling with large-scale computing, which today is linked to cloud computing, integrated by supercomputers of bits, and by the birth of quantum computers, and its marketing process. The current state involves the integration of edge computing, to implement highly complex mathematical models, this due to the growth of the power of the mini CPUs. Based on these concepts, HI has developed the artificial brain framework, composed of a neocortex, a hypothalamus, and a hippocampus. Like the human hypothalamus, the artificial one is responsible for guaranteeing the balanced development of a company, coordinating in real time, algorithms that act autonomously and process information in a distributed way. An artificial hypothalamus can be seen as the intelligent and autonomous coordination of algorithms, or as coordination of robots. So, the artificial hypothalamus, a part of the artificial brain, is the algorithm that controls the workflow of the models of the decision support system. It includes the constraints that guarantees that the system is in the optimal path. This is based on the duality theory. In real time, the concept of an optimal point must be replaced by that of optimal path, as the one who is always close to the ideal optimal points. More information about the artificial brain, it can get in the link in the PDF slides document. OPTEX is the way to make high-complexity large-scale artificial brains without programming. Normalization and standardization, the base of mathematical programming 4.0. The foundations of OPTEX database algebraic languages consider the algebra as a standard, to express the relationships between the different parts that make up a mathematical problem. It can be said that there is only a reduced way to write an algebraic equation. This is independent of the symbols that are used to represent the physical or logical relations. Additionally, if two algebraic formulas are joined, a new algebraic equation is obtained that retains the same structural characteristics of the original equations. This transitivity law may be extended to mathematical programming, MP, which in essence is a collection of algebraic elements. Then it is possible to join two MP problems to obtain a new MP problem. It is also possible to divide an MP problem into two MP problems. Then, OPTEX can easily generate a new model as the addition of two or more MP models, or as a variation of an existing one. On the other side, it is practically impossible that the union of computer programs generates a new correct computer program. The principles of transitivity between MP models, formulated based on a database algebraic language, can be extended to more complex structures, such as those derived from the partitioning and decomposition of systems to apply large-scale optimization methodologies. In this way, the new vision of mathematical programming involves defining the relationships between problems, as the next step after the definition of the equations that compose them. Resuming, if the formulation of algebraic expressions is normalized, it is possible to have a standard way of representing a mathematical model that can be understood by another mathematical modeler, making it a standard for formulating MP problems. Additionally, the combination, or division, of MP problems generates new MP problems, which can be solved using many optimization technologies. Therefore, to facilitate the development of models, it is convenient to establish basic principles, norms or standards, of modeling, in order to enhance the use of models and ensure that they remain current over time, thanks to conceiving as a dynamic structure that adapts to changes in computer technologies. This implies, previously to the implementation of mathematical models, establishing a standardization manual that guarantees the understanding of the mathematical model, by any professional knowledgeable about the subject. This fact will result in the portability of mathematical models and the significant decrease in the implementation time. Structured mathematical modeling is similar to assembling mathematical models like a Lego. A mathematical model stored in an information system can be conceived as the union of mathematical components harmoniously integrated. There are two types of components, or objects: basic mathematical definitions, indexes, sets, parameters, and equations or constraints; advanced concepts, problems, models, decision support systems, and artificial hypothalamuses. These components can be stored in a relational information system. It permits their handling in a modular way. Following the principles of relational information systems, and use structured query language, SQL, to manipulate the mathematical objects. This conceptualization is independent of optimization technologies, which allows to separate the formulation of the mathematical models from their implementation, using a specific optimization technology. The nuclear unit, the molecule, of a MP problem is the constraint, which is the result of integrating various types of atoms. Indexes, sets, parameters, and variables. Based on the constraints, more complex mathematical structures are built. Problems, sets of equations and/or set of subproblems. Models, sets of problems and/or set of submodels. Decision support system, set of models, and artificial hypothalamus. Considering that the problems are defined based on sets of constraints. If the modeler has built a database of equations, such as an equation store, he can formulate as many mathematical problems as the combinatorics of constraints that can be assembled. Traditionally, a problem is conceived as a monolithic set of equations. Under a modular conception, equations are components that can be shared by multiple problems. The important thing is that each equation works properly. This correct operation will be repeated in all the problems in which it is incorporated. If a store of equations exists, constructing a problem is limited to selecting the equations that make up the MP problem, and/or incorporate sub-problems that already have associated equations. This monolithic approach is easy to implement, however it does not allow the use of large-scale optimization methodologies. If it wants to use high-performance computing technologies, based on parallel processing, it needs to divide the mathematical model into multiple problems that represent the most elementary components of the physical system. This produces a significant gain in the solution time, and in the understanding of the inner operation of the system. To solve the model, it is necessary to select a large-scale optimization methodology that defines the processing of information in each problem. For example, the figure represents a mathematical problem related to the SAND-OP, sales and operations planning, that may be constructed based on 8 groups of equations. Production, energy, maintenance, distribution, sourcing, human resources, financial, and sales and marketing. The systems, groups of equations, that must be included in the SAND-OP problem depends on many factors, because there is no revealed truth regarding what the SAND-OP problem is. Since the equations are defined in a database, the configuration of a problem is limited to selecting from the equation store which are the ones that the modeler want to consider in the model. These visions can change within an organization. In this way, the modeler can have multiple SAND-OP models which depend on the use you want to give to the models. These models can exist permanently, or they can be created on the fly at the time they are required to be used. A decision support system must group all mathematical models, predictive and prescriptive, that uses the enterprise. Therefore, a DSS can be defined by the set of models that integrate it. Associated with the DSS must be the flow of information between the models, since it is logical that the output of one model is used as the input of another model. The traditional is that these models are used by users in a manual way, except in cases of advanced optimal control in which the models can run permanently, in real time, in an infinite cycle. An example of the architecture of a production DSS in an organization is presented below. It is made up of 8 models. The diagram describes the data flow between models. Traditionally, these models are run with a certain frequency, daily, weekly, bi-weekly, monthly, and the implementation of the decisions depends on the professionals who must validate the results. In some cases, this validation is automatic. The model's interconnection chain has no limits, which is necessary for an organization based on advanced analytics. The concept of model integration is applied in multiple dimensions. For example, an integrated oil company can be conceptualized based on the operation of 4 businesses: production, crude oil transport, refining, and transport of derivatives. In this case, the complete model of the company corresponds to the integration of the 4 models. For example, the figure represents a mathematical model for a multi-business enterprise that operates 3 business: electricity, oil and gas. The integrated model of the company will be the union of the 3 super-problems. However, the modularity of the modeling allows to have individual models for each business. These models can exist as an integrated model, or as 3 individual models, one for each filial. In this case, the data communication for the integrated multi-business model is defined by the Lagrangian relaxation methodology. Under a hierarchical conception, each subsidiary can be divided into sub-businesses that can be planned in a coordinate or integrate manner. Coordinating, when each individual model connects with another model to send its optimal decisions resulting from an isolated planning. Integrating, when all models are part of a holistic model that produces the real optimal decisions for the enterprise. When all the models that make up a company are solved using the concepts of real-time distributed optimization, an artificial hypothalamus of the company is obtained. This is how the human brain faces reality. Multiple models of reality, acting permanently in parallel, to make decisions. The algorithm that simulates the hypothalamus is assembled by OPTEX, using the models that traditionally make up a decision support system. Industry 4.0, intensive in data acquisition, extends the concept of real-time to any hierarchy of decision-making. Generating the concept of autonomous, real-time, distributed, optimization, in which multiple agents, distributed in the space, cooperate to solve an integral problem of the organization. An agent may be a country, a region, a business, an administrative department. The multiples models can run autonomously, activated by an exogenous event, for example, an earthquake, the failure of an industrial equipment, or by another model that requires processing their data. The artificial hypothalamus corresponds to a macro algorithm that coordinates the activation and solution of the models defined by the mathematical modeler. From the computational point of view, the models correspond to a set of microservices that solve problems and produce the required information, acting simultaneously and cooperatively. The concept of artificial hypothalamus can be applied to solve real-life problems from multiple points of view. In the diagram, the artificial hypothalamus coordinates models corresponding to the multiple problems faced by a company, organized from the point of view of its administrative functions. Another point of view is the spatial distribution of the problem. In this case, an artificial hypothalamus is presented for an agro-industrial company that has multiple facilities, farms, concentrated food factory, meat products factory, and stores in the food market. Making models in OPTEX is a task of coordination of components, not a task of computer programming. OPTEX supports all stages of the mathematical modeling process. Designing mathematical models from MS Word. The mathematical modeler can obtain computer programs in multiple optimization technologies without carrying out programming activities. OPTEX, Optimization Expert System, is a cognitive robot and expert system-oriented developed high-complexity mathematical programming. It was created by Decisión in 1991 and actually maintained by High. OPTEX is a rapid application development tool, focused on the design, implementation, startup, and maintenance of artificial hypothalamuses, conceived as a union of mathematical optimization models with information systems. OPTEX follows the modern guidelines of object-oriented programming, to avoid the intensive use of resources for programming computers, in the development and the maintenance of computing solutions. OPTEX is the new optimization platform. Its main general characteristics are: optimization information systems. The components of the model are stored in a database, tables of an optimization information system. As any relational information, its management is organized, standardized and normalized. This ensures control and the integration of models in an artificial hypothalamus customized for specific companies. Large-scale optimization. It manages the concepts of multi-problem optimization models to access of the concepts that support the communication between robots using mathematical programming. Optimization Expert System. Capture of knowledge and experience that store the mathematical components that work correctly in the information system, so that it is not necessary to rewrite them. The mathematical model is built as a Lego, selecting the proper components, the constraints. Capture the knowledge of a series of runs. Robotization. OPTEX writes programs free of errors in the optimization technology selected by the user. This means shorter development times. Changes to a model that works properly are implemented in minutes or hours. Freedom. OPTEX approach frees the mathematical model, algebraic formulation, of the optimization software, which is directly related to optimization technology like GAMS, AMPL, GMPL, OPL, Mosel, AIMS, C++, R, Python. Easy to use, complex models, using large-scale technologies, may be developed in MS Excel or MS Word, filling templates. A robot for mathematical modeling is aimed at replacing all the systematic activities that must performed by the mathematical modeler, during the development, testing, and startup of a mathematical modeling system. The end user, in the day-to-day use of mathematical models, either manually controlled by humans, or automatically controlled by an artificial hypothalamus. An expert system is an artificial intelligence that emulates the decision-making ability of a human expert. Expert systems are designed to solve complex problems by reasoning through bodies of knowledge, represented mainly as if-then rules rather than through conventional procedural code. OPTEX is working in automatic generation of systems of models oriented to build artificial hypothalamuses, that implies asynchronous parallel optimization, solving complex model using parallelization, real-time distributed optimization, optimization distributed in many agents that must work coordinated in real time. About information technologies, OPTEX provide automatic generation and maintenance of the metadata model of the input-output information system of the models. Automatic generation of a smart graphic user interface to link the user with the information system, using SQL statements to connect the models. Then the modeler doesn't need to know about information systems. OPTEX make easy to send the models to a remote optimization server where the mathematical problem is solved. Do you wonder of how to make high-complexity large-scale artificial brains, without programming? Making very large-scale models by the traditional way, using a computer programmer, it is an impossible way, because the programmer only can write a limited number of lines of good source code per period. Maintaining these models can be more complicated than doing them, if more than one programmer intervenes in the process. Considering that OPTEX is a cognitive robot, that implies that OPTEX is able to produce infinite lines of perfect source code per period. OPTEX interprets the implementation of a decision support system as the load of a relational information system, converting the mathematical modeling and the software production in a filling-the-blanks process. The LAN-WAN environment makes easy the simultaneous remote work of several modelers, using the power of Internet and the database servers. For example, each modeler can work on one of the submodels that integrate the full model of a company. With the time, OPTEX has a data warehouse that contains mathematical objects that have been proven in real models, and that can be used to build new models. This works in the same way that in object programming, where to make the software, the programmer can use objects that work correctly. OPTEX generates structured programs for each model. They are error-free and easy to understand, because the descriptions that exists in the database are included to the program. The multilingual capacity of OPTEX permits description in multiple idioms, then is possible to have the same model in different languages. The traditional process of mathematical modeling implies that programmers, usually mathematical modelers or data scientists, must make great efforts to implement complex optimization models. The OPTEX mathematical modeling process is divided into 4 stages, aimed to fill the tables of the Mathematical Model Information System, MMIS, and create and store the data model of Industrial Data Information System, IDIS. The stage are 1. Design and conceptualization, starting from the traditional formulation of an algebraic optimization model, the idea of how it should be stored in the MIS must be organized. 2a. Implementation of the mathematical model in the MIS. This process may be accelerated, if the algebraic formulation is organized into tables in the MS Word or MS Excel documents, used to write the model. 2b. Implementation of the IDIS data model to later create the relational tables that will store the industrial data. This information is stored in the MES tree. Generation of the optimization algorithm. OPTEX automatically performs this work, integrating to source code all the elements used by the modeler, such as, for example, large-scale optimization methodologies. The whole process comes down to filling the blanks in a template, or assembling a Lego object from components built by the modeler himself. The modeler does not realize programming activities, no need to know SQL. He must be an excellent mathematical modeler that understands the concepts of high-complexity mathematical modeling. OPTEX use the same structure to storage all the mathematical components that define a decision support system. Then, the mathematical modeler can use Excel or Word templates to fill the tables that integrate the MES. For implementing complex mathematical models from MS Word, the stages are: first, convert the algebraic model to a formulation in MS Word, in the form of tables. Second, convert MS Word tables into CSV files in standardized ANSI format. This may require an intermediate step that goes through MS Excel tables. Third, upload the CSV files to the OPTEX database. This process is carried out with the support of OPTEX, which automatically validates that the mathematical elements are correctly formulated. Fourth, generation of the source program of the mathematical model on the selected computational platform. The future OPTEX load process will be a more interactive activity via web access. Mathematical Modeling Information System. The entities handled MES are divided into. The basic components are required to make the equations of mathematical problems. They are indexes, sets, parameters, variables, equations, objective functions, planning horizons, and sectors. As an example, let's look at the process of storing information related to the indexes, or subscripts, that are used in an algebraic formulation. The diagram presents the process of converting a MS Word table to a SQL table that understands OPTEX. As a design norm, typical of relational information systems, associated with any object, or entity, there is a master table and a set of tables that store the relationships of that entity with other entities. The screenshot shows an image of the indexes master table. Then, the modeler can explore the mathematical modeling database, following the principles of the relational information systems. The screenshot presents the master table of indexes, and all the tables with relationships with other entities, like variables, constraints, parameters, aliases, problems, data tables, and fields in the data tables. This vision implies thinking outside the box, since the relationships between mathematical elements are not investigated in the computer programs, but they are visualized in a holistic way through the exploration of a database. The process for all MES entities is similar. From an MS Word table the OPTEX database is loaded. The diagram presents the case of read sets, which includes as data the link with the data model of the Industrial Data Information System, IDIS. From the data stored in the database, the programs associated with the algorithms of the mathematical problems are generated. The screenshot shows the case of the read parameters. For the calculated parameters, it is necessary to store the formulas in a structured way, in order to facilitate their analysis as a structured data. The screenshot shows the master table of variables, and the one related to their indexes. This data is used by OPTEX in the computer program's generation. The load of the equation includes its algebraic formulation. To be stored in a structured way, OPTEX performs the conversion automatically, from the formulas defined in the MS Word document. The advanced components correspond to mathematical structures that are made from the equations. They are problems, models, decision support systems, and artificial hypothalamus. The problems are defined by equations and other problems, which in turn are defined by other equations. A problem is associated to a format, like linear programming, nonlinear programming, etc. Similarly, the models are defined by problems and other models, which in turn are defined by other problems. When defining the problems of a model, it must specify how they are related in the solution process. For example, a model based on Bender's partition theory requires specify which is the coordinator and which is the slave. OPTEX generates RTF documents, visible and editable with text editor programs like MS Word. The RTF contains all the mathematical formulation and the IDAS data model, including the link between the fields of each table with the sets and the parameters that are read as input data. Thus, OPTEX guarantees proper documentation of the implemented models. The data model of the User Industrial Data Information System, IDIS, has a bi-univocal relationship with the mathematical models. This is taken advantage of by OPTEX to automatically generate the data model of the IDIS, and the user visual interface, based on a system of holograms for the data capture screens. This is taken advantage of by OPTEX to automatically generate the data model of the IDIS, and the user visual interface, based on a system of holograms for the data capture screens. The first point to consider is that the indices of mathematical models define the entities of the data model. Additionally, the relationships, sets and indexes, parameters and indexes, variables and indexes, and restrictions and indexes define the relationships between IDIS entities. Based on these laws, OPTEX can automatically generate the IDIS data model, considering the sets and the parameters to be read. OPTEX manages a metadata model that, automatically, generates a user interface that includes an Explorer menu to navigate the tables of the IDIS that can be resident on various types of database servers. Second, all the shell windows that contain the master and the relations tables for each entity. These components, browser menus and windows, are not associated with any program. They are generated by OPTEX, online, when the user requires them. To store all the results of the runs of the models, OPTEX automatically generates the structure of an extended information system, based on the scenario and scenario families concepts. All result tables are stored in normalized relational tables. Regardless of the programming languages, the models connect directly to the IDIS database, by means of SQL statements. Because the IDIS data model is open, the end user can connect it to any other application developed by a third party, this for any input-output data. The screenshot presents SQL connectivity in a GAMS program. The screenshot presents SQL connectivity in an IBM OPL program. The learning process of the human being is concretized in memory, which accumulates information, data already processed, to face each new situation, using the knowledge stored that has been made up to that moment. This knowledge is stored in the hippocampus where the data is organized according to its age. Like any physical element, its use affects its reliability, and that is why short memory, the one that stores the data of the last moments, begins to fail with age, until it is lost, while long-term memory can store very sharp data, but that require greater access time to locate them. It could be said that, to support decision-making, the artificial hippocampus stores historical information related to the models formulated and that work correctly, and the runs made with a certain model, in such a way to be able to use this information in new runs. The first case has already been analyzed throughout this presentation. For example, a basic artificial hippocampus can be constructed using Bender's partition theory, which can be interpreted as the general problem is divided into two complementary subproblems, an experimenter, that makes decisions in real, or in simulated, environments, and that send the results to the higher level, and an information manager, that stores the results, sent as primal and dual variables. when it is required to make a real decision, or to perform an experiment. The information manager processes the stored data to determine two zones with respect to decisions, a desirable zone and a non-desirable, or utopian, zone. Mathematically, this is done by generating cutting planes and incorporating them as part of the information to be processed. The experimenter receives the information from the manager, makes decisions, and sends the results to the manager. The speed with which this loop is made can be that of an algorithm that does not stop until it finds the optimal solution, or that of a human who makes decisions step by step. The first non-optimal zone that contain values of the decision variables that must be discarded because they cannot be optimum. From a human point of view, it contains decisions that should not be taken because there are better. The second non-feasible zone that contains values of the decision variables that must be discarded because they cannot be feasible. From a human point of view, it contains decisions that cannot be taken because they are impossible. Decisions not included in the two zones determine the area of rationally desirable and possible decisions. Following the principles developed by Benders, it is possible to build an artificial hippocampus that remain active and useful beyond the duration of a run of a computer model. To do this, the cuts generated in each run must be stored in such a way as that they may be used later. This implies a coordination work, since it cannot be guaranteed that the information as it is produced can be reprocessed later. OPTEX, as an expert system, stores the cuts of one run to be used in the next, which will produce new cuts. HI is researching in the creation of methodologies to generate new rules that fit the dynamic variation of the parameters that affect the models. Another alternative to generate knowledge that is stored in the artificial hippocampus is the generation of convex hulls associated with optimal solutions of the mathematical problems. The multidimensional grid that represent the convex hull can be incorporated into the integrated problems to accelerate the solution process. Depending on the specific problem, the convex hulls may be permanent, or they must be recalculated dynamically when the parameters of the mathematical models change. Convex hulls allow flexible approaches, as in the case of an energy transmission system, in which they can be associated to two different ways to solve the problem: flow AC and DC flow. The production of convex hull of optimal points is a standalone process, therefore they can be generated outside the optimization process. The table shows the OPTEX solutions, decision support systems, developed using OPTEX. It is suggested to use the index in the PDF slides document to navigate directly to topics of interest. Like Herbert Simon, Hypothalamus AI believes that the computer-based mathematical modeling is the greatest invention of all times. Thank you for your attention.